Hi, thank you, Dr. Bragnito, for your kind introduction. So I'm Dehao, and I'm right now a postdoc at the TAMIDS in the Scientific Machine Learning Lab. Today, I'm going to talk about the physics-constrained neural network with Minimax architecture for predicting the microstructure evolution. So before I move to the methodology, let me give you some introduction why we are doing that. So as you know, the metal additive manufacturing is kind of the transformative technology by which metal parts are printed layer by layer with high energy laser or electron beams. So one of the biggest advantage of the metal additive manufacturing is that it can significantly improves the manufacturability of metal parts with complex geometries and heterogeneous materials. Therefore, metal additive manufacturing has various applications in different industries, such as biomedical, aerospace, automotive, energy, and high-value, low-volume industry environments. And however, the current research change for metal additive manufacturing is that the lack of the complete process structure leadership. So as we know that for different processing parameter, we have the different microstructure, and those the different microstructure like the grain orientation, grain size distribution, they will affect the final properties of your printed parts. And if we don't have this complete process PSP relationship, we cannot produce the printed defect-free, structurally sound, reliable end parts. We will have these defects in our printing parts, and this is really bad, and we want to avoid this. And however, as you can see, for this PSP relationship is a really high-dimensional relationship in this material science or this manufacturing process. And this is caused also the well-known the curse of dimensionality in the design space. Because when you increase the dimension of the design space, your training data will quickly become sparse and overfitting can occur. So how can we handle this curse of dimensionality? Because for complex engineering program, we don't have enough training data for the metal additive manufacturing. So the motivation for this physical constrained neural network is on the one hand, only relying on the physical basis models, the simulation like phase field model, the stereo automation model, the finite element methods, so on so on to construct this PSP relationship requires a lot of the prior physical knowledge, and the forward prediction can be very slow. On the other hand, only relying on the machine learning models requires a lot of the significant amount of training data to construct this PSP relationship. And however, we don't have enough training data for metal additive manufacturing. And also, for machine learning, it's a purely black box, and it doesn't have the high physical interpretability. So the question is how to construct a data efficient and physically interpretable machine learning model for fast forward predictions. So the answer is a phase-constrained neural network, or the PINs. So since Dr. Bragnito already talked about this PINs, I will just give you a quick route. So we have the artificial neural network, and then we take the auto differentiation, we get the derivative, and then we embedded the physical constraint into our loss function. And however, for this the baseline PINs, the weights for different losses, they are constant. So, or they are empirical adjusted. So because the weights of the different loss terms, it will implies the importance of your training data or your prior basic knowledge. So you really want to adjust the relative importance of these different terms, because they will affect the convergence of your neural network, and it will also affect your generalization ability of your neural network, of your machine learning model. So how to systematically search the weights of the different losses? So our answer to this question is the physical constrained neural network with Minimax architecture. So what is that? And the training of the PCNMM is to solve the Minimax problem. So which means we maximize the loss in this alpha subspace, and this alpha is basically the parameter in the weights of the different loss terms. And then we also try to minimize the total loss in this W subspace so that we can solve this Minimax problem. And solving this Minimax problem is essentially to search the high order saddle point in the energy landscape of your objective function. So which means for this saddle point, we are trying to search the local minimum in this W subspace, and we are also trying to search the local maximum in this upper subspace. And there are two research changes here. So one is the objective function could be non-convex in this W subspace and concave in this upper subspace. The second change is that we need to search high order saddle points rather than the first order saddle point. So the order here means the number of negative eigenvalue of your Hessian matrix of this objective function. When you have one negative eigenvalue of your Hessian matrix, you search the first order saddle point. But if you have two or more the negative number of the eigenvalue, you are searching the high order saddle points. And we developed a new generic high order saddle point search method called the Dehao method, so that we can search this high order saddle point for this Minimax problem. And the main idea of this Dehao method is we are trying to use the extreme eigenvalue and eigenvector to guide the search of the desired saddle point for this problem. So this here, the extreme eigenvalue in your Hessian matrix can help you to guide the search. So let me give you some example. So as Ming already said, the solving the one-dimensional Invis-Burgers equation can be really tough. And here we demonstrate the power of our physical constraint neural net with Minimax architecture by solving this one-dimensional Invis-Burger equation, and you can solve this one very well, and it agrees with the true solution. You can see that here we didn't add any viscosity coefficient here. And this is another example. We are using the physical constraint neural network with Minimax architecture to solve the one-dimensional Elencan equation. Elencan equation and Elencan-Hilliard equation, they are very well known in the microstructure prediction simulation, because and as you can see here, the physical constraint neural network with Minimax architecture cannot solve this title of the equation very well. There is a big gap at when x equal to 0, and then we turn to our attention to this self-adaptive bint, which is developed by the Levi and also Dr. Bregnito. And then when I try to use the self-adaptive bint without this hard constraint, it cannot really converge, and the solution is not very good. So I embedded this hard constraint of the initial condition, so that this initial condition can be satisfied perfectly. So here you can see the prediction can agrees with the true solution here. And also here you can see how the weights of at a different location of your cooptation point and also the initial boundary points are weighted here. And we also use the one physical constraint neural net with Minimax texture to solve this one-dimensional Hilliard equation. You can solve this pretty well, and we then turn to our focus to this high-dimensional physics problem, and we use the physical constraint neural network and physical constraint. It turns out that as you can see, the first figure shows the finite solution of this heat transfer problem. And when we use this simulation data to train the artificial neural network, the prediction from the artificial neural network is far away from the finite solution. And when we added the physical constraint into our total loss function, it turns out that the physical constraint neural network are more accurate than the artificial neural network. And the Dehao method can also provide additional eigenvalue information to make sure we find out the desired saddle points. And then we use the physical constraint neural network with Minimax architecture to solve this two-dimensional Hilliard equation. So basically, this represents the spin nodal decomposition process. And when we only consider the physical constraint without any training data, and you can see here the first figure shows the solution from the FFT. And the second figure shows the prediction from our physical constraint neural network. And you can see that if we only apply the soft constraint of the initial condition, that the prediction from the PCN is not very good, and so we turn our focus so that can we add this hard constraint. And when we add this hard constraint, you can see that the prediction from the physical constraint neural network, there are some it just maintains the initial condition, because for the initial composition field, there are just some random fluctuation of the composition field, but it cannot involve. So it cannot, for this physical constraint neural network, you cannot predict the time evolution of this composition field. So you cannot really capture the dynamics of this spin nodal decomposition. And then we use this two-dimension. We only use the artificial neural network to predict this phase transition without any physical constraint. And you can see that we only use the first 80% of the time series data to train our artificial neural network. And you can see that at the beginning, the artificial neural network can capture this phase transition at the very beginning, but when you try to do the prediction outside of the training data, you are doing the extrapolation, and the prediction of the phase field is far away from the true solution. So this is not the ideal solution. And then we add combine the training data and physical constraints. So we train the physical constraint neural network. And this is our prediction. So from the time equal to 0 to the time to 0.02. And you can see that if you just focus on this small area, the phase field will evolve, try to become larger and larger, and then those phase field will combine with each other, which means that this physical constraint neural network really capture the dynamics or physics of this spin nodal decomposition. However, for this physical constraint neural network, the initial distribution of the composition field or phase field is wrong, and because it cannot capture the initial phase field, so that the time evolution or the final phase field is far away from the prediction. As you can imagine here, we only apply this soft physical constraint, so it cannot guarantee that those physical constraints can be satisfied perfectly. But on the other hand, if you are trying to apply those hard constraints of the initial condition, and the physical constraint neural network cannot really learn the dynamics or the time evolution of the phase field. So there is a trade-off here, and I think that the soft constraint. The soft physical constraint can provide more flexibility to the physical constraint neural network, so that the physical constraint neural network can learn the dynamics of this microstructure evolution. And then we switch our focus to this multiphysics problem, because for a lot of the microstructure evolution problem, they are multiphysics, and a lot of the engineering problem, they are multiphysics, and that multiphysics problem could be more challenging for Bing to solve. And the change comes from this couple physics, because they will cause the unstable chaining. So if we are using this concurrent training scheme, which means like we use the multiple neural network to train, we train the multiple neural network to predict the multiple physics field at the same time. And which means for this complex system, the training will become very unstable because those physics are coupled with each other. So instead, we developed a new training scheme called the sequential training scheme. So in this sequential training scheme, we have the two neural networks. The first neural network will be trained to predict the first physical field like U, and this physical field will be feed to the second neural network for the training of the second neural network. And by this way, the multiphysics can be partially decoupled and the training can be more stable. And this is our training results. So for this, the single density problem is a 3D physics problem. It involves the heat transfer, phase transition, and through transport. And the first column of figures here shows the simulation result from the phase field simulation. And the first row, it shows the phase field, and the second row shows the composition field. So as you can see here, the sequential training scheme, the prediction result from the sequential training scheme is the best. And however, you can see the secondary arms cannot really match the secondary arm of the simulation result. So there are still a lot of the opening change and question to for the pins to solve this multi-physics program. And so to summarize our work, we developed a data efficient and physically interpretable neural network, and we developed a new physical constraint neural network with Minimax architecture to adjust the weights of different losses systematically. And we established a new sequential training scheme to add the convergence of the physical constraint neural networks. And so our future work, we want to understand more about the training dynamics of the physical constraint neural network, like when and why these pins will fail. And like we may want to use like the neural tangent kernel to understand the training dynamics of the pins, so that we can take a look at this gray box, like what's going on, how is the convergence of this physical this pin is affected, and how can we improve that? And we also want to develop a new training method for pins, so that it can solve or predict it can solve the Elencan and the Kahn-Hilliard equation better, because I'm mainly interested in this microstructure evolution problem. And we also want to quantify the uncertainty of the prediction from the physical constraint neural network and Minimax probe. So to just give you some thoughts, so my thoughts about why this physical constraint neural network fail for solving this Elencan and Kahn-Hilliard equation. There are multiple possible reasons. The first reason is that we only apply this to solve the physical constraint, so that the physical constraint cannot be satisfied perfectly. And the second one is called a spectral bias, because for physical constraint neural network, some existing work has shown that pins tends to converge faster for some low frequency term, but it cannot really capture those high frequency term to learn the dynamics. So there is some spectral bias. So it's a really tough problem to resolve. And the third change is how can we solve the multi-physics problem using the existing pin framework. So we need to develop a new architecture or new training algorithm. And I'm open to any question, and hopefully you can give me more insights or suggestions for my research. Thank you.
Thanks, Dehao. Look, this is probably the toughest challenge for pins. Yep. You know, these phase field models, is particularly two-dimensional models. They're already tough in 1D, but you know, in 2 dimensions, they are. It's an extreme challenge for pins, and that's why it's a good problem. You know?
Right, that's true.
And obviously, yeah, one of the things that we're gonna have to study going forward is how to introduce more physics into the neural network.
Right.
You know, in addition to the PDEs, of course, any conservation laws or any further physics constraints, and obviously how to improve the training procedure. This is a big challenge across the board. Yes. People are studying, you know, like you mentioned, the neural tangent kernel and other methods like this to understand training, and then to actually be able to improve the training process, which is still not really well understood.
Yes.
It's not well understood in deep learning in general, much less in physics informed deep learning. So this is a big area of opportunity for research for everyone, is how to improve the training process. And but I'm sure that we're going to make progress in this, because like I said, it's a big area of opportunity. There's not much. There's some, but not a lot in how to improve the training of this. So any questions from the audience? So we are very happy to have this collaboration with Raimundo Royavi and his group and Dehao, because like I said, this is I think one of the most challenging problems, and one one of the problems that can yield the best results, the best fruits for scientific machine learning.
Yes, so, I just wanna second that. I'm also very excited about the collaboration. And for material scientists, the microstructure problem is the fundamental problem. This is how we understand materials. So, this is a very challenging problem, but making some progress, in this direction will have very high impact in our field.
Yes, absolutely. Thank you. So, any more comments?
I just have one question, Dehao.
Yes.
When you are you showed that Minimax problem, PCN Minimax, and then you define this lambda as a function of alpha terms, and then you are going to learn alpha, right?
Right.
So this will define the weights of each loss function term. This is very interesting because for me it's always tough and a mystery. How can what values I'm going to use as weight, and
right.
keep trying. It's very time consuming, but what is exactly the function lambda? For example, this lambda t alpha. What is this function? You are learning the value itself, or you are learning a function, a parameter of this function?
So we are learning the parameter alpha for this function. So for this function form, we are using the softmax function for this lambda. So because the advantage of the softmax function is that when you add the softmax function together, you will get 1.0, which means that they are already normalized already.
Oh, I see. Softmax.
Yeah.
Perfect.
Yeah. And for the softmax function is kind of like non-concave function somehow. So you will learn get some good properties from there. Yeah. And also, if you are if you want to go further, maybe you can also take a look let's see from here. Dr. Breck-Nito's work, they introduced the max at different points. So for the different your training data or your collocation point, actually you are introducing max, the lambda r at different points. So they are point-wise max rather than as me, I just put this lambda function at a different loss term. So there are different ways to embed this max in your loss function. Okay, so the main idea or the key ideas of this min-max formulation is that you want to train the neural network to learn the importance or the attention of this different loss term, right? You don't want to assign the importance or the attention by human. You want the neural network to learn the relative importance of different loss term or the different collocation point by themselves. Yeah, that is the main idea of the beauty of this min-max formulation.
The interesting thing is that you know, we came to these ideas independently. So you know, Dehao was doing his work at Georgia Tech, and he came up with the Minimax for the weights. We also came up with that idea for the individual points. But this was completely independent. And then, of course, I learned about his work, and then that's when I really thought he could make a big contribution here, because, you know, I like this idea.